Magnetic Field of a Bar Magnet by Justin Siegel. So the purpose of this experiment was to measure the distance dependence of a magnetic field due to a bar magnet. We also want to compare the observed values to the computational values determined by glow script. So there were three main principles used in the experiment. The Diaz-Savart law, which states which is the magnetic field produced by an object at an observed point, as you can see by the top equation, the on-axis magnetic field equation, which is at the bottom, and the distance dependence equations, which are in the middle. So for our overall results, the magnitude of the magnetic field increases as distance decreases. The magnetic dipole moment was seen to be 3.23 ampere times meter squared. The observed off-axis magnetic field is 6.37 times 10 to the negative fifth Tesla, and the calculated off-axis magnetic field is 3.71 times 10 to the negative fifth Tesla. For this experiment, we had to make some assumptions, which included the magnetometer was properly set up, there was no magnetic field interference from anything besides the magnet and the Earth, the phone was held still and stayed still, and the measurements were accurately recorded. So for this experiment, the system was the magnetometer, or the phone, and the surroundings were the bar magnet and the Earth and everything else in the room. The initial conditions were that the phone, or magnetometer, was on a flat surface until the X component was at 0. So for this experiment, first the phone was placed on a flat surface and adjusted until aligned with Earth's north and south magnetic poles. Then a ruler was aligned below the phone horizontally and a magnet was placed to the left. The magnetic field was measured from a magnet at different points, starting on axis, then moving all the way to 45 degrees off axis. So for the experimental report, question asked to us was which of these statements described what you observed, and I observed the first one. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the X direction. And the last one, as the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases. So here are my experimental results. As you can see in the top left in the yellow, those are the distance in meters and the magnetic field in Tesla. And then at the bottom is the off-axis field, as you can see the calculated distance and the calculated net magnetic field, which is 6.37 times 10 to the negative fifth, which I stated earlier. Here is a graph created, and this y equals mxb equation will come in handy further on in this presentation. So here is a big calculation done to determine the magnetic dipole moment. As you can see, here are the two magnetic field equations set equal to each other in order to determine the magnetic dipole moment, or mu. So using the y equals mx plus b formula, we were able to determine that n equals negative 2.6066, and that k equals 6.46 times 10 to the negative 7. So overall, mu equaled 3.23 ampere times meter squared, as stated earlier. Here are the computational results. As you can see, the arrows for both on-axis and perpendicular, as well as the magnitude of the magnetic field at 45 degrees is 3.71 times 10 to the negative 5, which was stated earlier. Here's the glow script code for that model. The arrows had to be adjusted a little bit. Their scalars were increased a little bit so that you could see them. The perpendicular and the parallel arrows were all created, and the magnitude as well as just the magnetic field were all printed out. So for the additional questions, the first one, the concluded results would be incorrect, and the x and y components would vary depending on the angle created from the true north, which would no longer be 45 degrees. And also the difference between the observed and calculated results would increase because the calculated results are supposed to be as close as possible to the observed results in perfect conditions. And for the second question, the net electric field would increase due to superposition, but the direction would stay the same. So for our conclusion, the main sources of error would be the potential movement of the phone or magnet during the experiment, other magnetic fields affecting the phone, and measurement errors. An overall conclusion is that due to distance dependence, the x component of the magnetic field increases as the magnetometer gets closer to the magnet. Earth's magnetic field has a large effect on the calculations, and the calculated off-axis magnetic field was smaller than the observed one, but not by a large margin, which means the experiment was completed almost to perfection. Thank you.